TFS Hydraulic and Fluid Applications number 59. Since diameter of pipe was not given, I arbitrarily selected 2 inches. I proceeded with the calculation and got C. Why is this not a viable solution? So this problem was about a parallel piping system where we were given a little bit more information about some of the losses. One side had a valve and a coil and straight pipe, and the other side had a valve and a coil and more linear feet of piping. So it's a pretty interesting problem, and we had to set it up that the losses are equal through each path, which is typical of a parallel piping arrangement. But to your point, the diameter wasn't given, and in the solution that was offered, this is the typical solution for a parallel piping arrangement. We say that one path is A and one is B, and we say that the losses through path A are equal to the losses through path B, and then we expand on that by writing the Darcy equation. So FL sub A V sub A squared over 2dg equals FL sub B VB squared over 2dg. And in this particular problem, the friction factor, we were meant to assume that it was equal, and the diameters are the same. We don't know what they are, but they're the same. And that cancels out. And then obviously 2 and g are both constants, so those cancel from both sides. And we're able to derive a relationship between the velocities and the linear feet. And for the devices that are in line, we can turn PSI into linear feet as well. And that was kind of the key to moving forward in the problem. If you assume a diameter, the problem with that is that later on, you're going to calculate the velocity, and you're going to use this relationship, Q equals VA, velocity times area. And if you've chosen a pipe that's too small, then your area will be small, which means your velocity will be big for a given volume flow rate. And the opposite is also true. If you choose a pipe that's too big, then your area will be big, which means your velocity will be too small for a given flow rate. And it has to be true in a parallel piping because it's going to come back together. This relationship has to hold, that QA plus QB has to equal the total, which in this case was 50 GPM. That's non-negotiable. So there's an interplay between the area and the velocity that's unavoidable, and that's going to come to bear later in the problem. So what we really want to do is abstract out not only the diameter but also the velocity. And the way that I do that in the solution is I rearrange this expression so that we get, I'll skip some of the steps here just so it's not becoming long-winded, but we want to get VA over VB. So we get everything on the other side, and then we don't want it to be squared, so we take the square root. So that ends up equaling LB over LA square root. And then we use this idea that Q equals VA, and since they have the same diameter, they have the same area. So the relationship between QA and QB is the same as VA over VB. So we can make that substitution directly into here and say that this LB over LA under square root is equal to QA over QB. And now we don't need to work with the velocities at all. We don't care what the diameter is, and we don't care what the velocities are. We are now able to have this expression that relates the flow rates, which we know something about, right? This is information that absolutely has to be true for a parallel piping arrangement. The sum of the flow through the two paths has to equal the total flow. And we have information about the linear feet on each of the two runs. So this left side of the equation is known. So if we have the value of this ratio and this equation, we have two equations with two unknowns. We now have an algebra problem, right? This boils down to x plus y equals a constant, call it a, and x over y equals another constant b. So just, algebraically, this is doable. So that's the process that I wanted you to go down. And I guess coming back to your fundamental question, like, why can't you just arbitrarily pick a diameter? I guess it's okay if you arbitrarily choose a certain diameter that's the right diameter. And now I'm wondering if you could actually figure out a way to work backwards once the volume flow rates are known to figure out the velocities. I wonder if you could. I don't know if you could. And then figure out the diameters, and then maybe Maybe there's a correct diameter that makes it all work, and if you were to guess correctly, then you'd be good, and if you didn't, then you would not. I'm not sure if that's true. But what I would invite you to try as a way of exploring your question is to make different arbitrary selections. Try 3 inches, 4 inches, 5 inches. And if every time you try a different value for the diameter, you get a different area, which gives you a different velocity, which gives you a different flow rate, right? Just kind of redo the exact process that you went through with different starting point assumptions. And if you get all different answers, and the answer's jumping all over the place, then it can't be an acceptable approach, because there can only be ultimately one right answer. So that's my suggestion, and you probably don't actually need to try multiple. You could just pick one other value, and if that changes the answer at all, then you know you can't go down that path.